Hello, my name is Alicia Maria Gal, and I'm a doctoral candidate for the Ottawa Carleton Institute of Biomedical Engineering. I'm a Nipissing University Distinguished Alumni, Queen Elizabeth II Diamond Jubilee Advanced Scholar, NSERC Create Ready Trainee, and the biomechanics coach for Ravens Varsity Soccer. My research focuses on quantifying body motion for the purpose of performance enhancement and injury prevention. Please enjoy this presentation entitled Potential for Autonomous Linear, Curvilinear, and Phase Detection in Natural Context Pair Skating using IMU sled motion data. Thank you to our research funders, NSERC Create Ready, and NSERC Engage Research Partnership with our industry partner, Tritonware. The ability to quantify gameplay is a sought-after capability for the vast industries that create the sporting world today. Player performance analysis during natural context scenarios can provide game-changing information for program optimization, performance enhancement, strategic growth, and injury prevention. Qualitative analysis is defined as systematic observations and introspective judgment. Proper quantification of performance involves systematic approaches via biomechanical mathematical models. Fundamental biomechanical principles, such as phase analysis, temporal analysis, and critical features, provide quantitative performance analytics. There is a need to integrate biomechanical principles as an international standard when teaching, coaching, and conducting research involving qualitative applications of performance assessment. Properly designed algorithms can provide frameworks executing systematic observations of performance in order to gain quantifiable data. Lack of understanding the signal is a major drawback for autonomous algorithm development. Efficiency and effectiveness rely on proper development of the expert system. Systematic progressions through forward chaining allows the inference engine to develop a biomechanical appropriate knowledge base. Obtaining valid, reliable, and efficient quantifiable natural context sporting data is a gap that may be filled by emerging technologies such as inertial measurement units, IMUs. This paper focuses on examining the use of IMUs in the sport of para ice hockey. Data collection occurred within regulation ice hockey arenas, complete with pre-session participant screening and anthropometric-based interviews. Additional session data was manually recorded by research assistants. Participants were 2 expert para ice hockey players who identified with an impairment, and a total of 5 impairment-free task-naive participants, 2 males and 3 females. Waterproof IMUs from Tritonware acquired data problem-free in regulation ice hockey arenas at a frequency of 51.2 Hz. This data was used during autonomous algorithm detection. Ground truth was human-derived via the video from the Tritonware application. IMUs were centrally located on the backrest and underneath the bucket of the on-ice sledge in a non-damaging fashion. IMU sledge location was considered crucial as the body and sledge may move separately during skating. 42 linear pair skating trials were analyzed during this study. Linear skating tests consisted of 2 short distances, blue line to blue line, and goal line to blue line, and 1 long distance, goal line to far hog line. 36 curvilinear pair skating trials were analyzed during this study. 90-degree turn tests consisted of 2 directions, a turn to the left and then a test to the right. 1 expert player performed start-stops between the blue line and nearest hog line. A total of 105 trials were analyzed in this study. 2 autonomous algorithms were developed. First, a linear detection algorithm was developed to gain skating analytics such as stroke count. Raw accelerometer data was converted into acceleration. A Gaussian smoothing function was used to create a more realistic human motion waveform. A simple search peak method was used to find local maxima for stroke count. A preliminary peak threshold was set at 2.5 meters per second squared, as not all participants were able to sustain or create elevated peaks during linear skating trials. PicPlant was used to eliminate duplicate peak counts within 1 stroke cycle, as well as indicate stroke boundaries and trial end. Next, a turn algorithm was developed in order to differentiate between linear and curvilinear skating tasks. Raw gyroscope data was converted into IMU orientation rate of change. This was followed by sensor fusion in MATLAB using both acceleration and converted gyroscope data to gain IMU orientation in degrees. Biplanar motion in the transverse plane is the motion of focus when determining a turn. A moving mean was used to differentiate between the orientation of the current location and the orientation about 2 seconds ahead to determine if a turn occurred. A turn was defined if IMU yaw orientation exceeded 20 degrees. This preliminary threshold allows for the body's natural sway along a plane of progression during motion. The autonomous linear algorithm was able to determine stroke count for 100% of the trials analyzed. From the data, on the left, the expert produced elevated amplitudes, narrow widths, and symmetrical skating patterns as compared to the task-naive signal on the right. From this data, we can see that the potential for IMU capability to differentiate between skating skill level is there. As previously stated, multiple peak count was eliminated per stroking cycle via a simple pick-plant location comparison. Again, pick-plant was also used to distinguish the end of a trial. The autonomous turn detection algorithm was able to correctly distinguish between all linear and curvilinear skating trials, 105. From the plots above, our expert is on the left, our naive is on the right. Our right axis, delta yaw average, represents the blue line. It is the change in orientation from 2 seconds ahead of our current location. We can see from the 2-second window in purple and the 20-degree turning boundary, gray, that the expert skater produced a much more rapid and fluent turning pattern compared to the task-naive on the right. From the task-naive participant, we can also see that turning during unstable motion creates a complex waveform. Again, this demonstrates the potential of the IMU to differentiate between skating skill level. Furthermore, from the data on the right, we can see that a 2-part turn occurred during the naive trial. From the blue line, peaks between 2 and 4 seconds and 6 and 8 seconds distinguish a large change in direction of IMU orientation. From the videos below, we can see that the bucket of the sledge slides across the ice through the turn as opposed to carving the ice like the expert on the left. IMUs are affordable motion tracking devices that show great potential to quantify natural context performance, specifically in high agility motions like pair skating. Performance analysis tools like IMUs and their algorithms can provide supportive information such as momentum during motion, which can be game-changing for any athlete. Developing a deeper autonomous neural network by integrating key observable gait parameters such as symmetry, fluidity, imbalance, and positive habituation would be paramount for any athlete development, especially the para-athlete. Para-athletes have unique physical limitations, and individualized assessment would be game-changing for their athletic future. This current algorithm shows great potential for aiding multiple para sports which use similar bibrachial stroking patterns like we see in our video with para rowing. This study concluded that centrally located IMUs on base equipment is an acceptable location to acquire para motion. Waterproof IMUs are problem-free in regulation ice hockey arenas despite the close proximity to the ice surface. There is great potential to gain performance analytics from IMU data with the proper development of autonomous algorithms. The ability to quantify predominantly qualitative performance indicators will aid in sport development as a whole. The ability to quantify skill level is game-changing. This study is not without limitations, such as IMU device limitations as baseline drift, drift from prolonged use, and secondary axis verification. Next-generation algorithms focus on creating the ability to differentiate between multiple tasks, such as stroke count in a turn. Simple modifications already implemented into the algorithm show great potential for autonomous multitask detection. Again, implementing stepwise biomechanical principles within the algorithm allows for systematic observations to be concluded effectively and efficiently. I will leave you with this thought. If we knew a little more at the beginning, it would have made it easier. Then maybe we would have tried again despite our struggle. I would like to thank my research team, especially my on-ice research assistants, all of our participants, and of course, the funders that made this research possible. NSERC Create Ready training program and the NSERC Engage research partnership with our industry partner, Tritonware. Thank you, and I hope you enjoyed. Any questions?